Welcome to the Deep Dive, the show where we distill complex, fascinating source material into truly mind-expanding nuggets of knowledge. Today, we're plunging into a question that has quietly puzzled philosophers and physicists for centuries, actually. And it's one that could fundamentally reshape our understanding of, well, pretty much everything. What if everything we thought we knew about the fundamental nature of reality, and especially the very origins of mathematical and physical laws, what if it was incomplete? Imagine, if you will, a single foundational principle, something so profound that it could unify paradoxes stretching from the bizarre counterintuitive world of quantum mechanics
Yeah.
all the way to the seemingly simple yet notoriously problematic definition of zero itself.
It sounds a bit like science fiction, doesn't it? Almost too grand. But that's precisely the audacious claim we're going to explore today. Our mission is to take a deep dive into an extraordinary new theory, invariant omnilectic mathematics and coherence-based physics. And look, this isn't just a slight adjustment to our current models, not at all. This framework posits something truly revolutionary, that coherence, not randomness, not even entropy, is the underlying generative logic of reality. It's a fundamental rewiring, really, of our cosmic understanding.
That is a radical departure from conventional thinking, to say the least. So this isn't merely about doing math differently or, tweaking a few physics equations here and there. It's presented as an entirely new ontology, a deep dive into the very nature of existence and how mathematics and physics were profoundly, almost inextricably interwoven. We'll be uncovering the meticulously layered architecture of this framework known as the Unified Coherence Theory of Everything, or UCTE. Our goal today is to understand how reality coherently constructs itself, step by coherent step, from the most abstract pre-emergent principles down to the very particles and interactions you observe every single day. So yeah, buckle up, because this is going to be quite the journey into the foundational layers of existence. All right, let's try and unpack this incredible premise. Our sources kick off by telling us that classical mathematics and physics have, in a very real sense, hit a wall, a kind of conceptual limit. They've reached conceptual and formal limits that prevent a truly unified understanding of the universe. We're talking about those persistent, deeply frustrating inconsistencies that keep popping up, the mind-bending paradoxes in set theory, like Russell's paradox, the unresolved mystery of quantum measurement, where the act of observing seems to fundamentally change reality, and that tenacious conceptual chasm between Einstein's general relativity, describing the macro universe, and quantum mechanics, describing the micro. It truly feels like we've been trying to force square pegs into round holes for a long time, doesn't it? As if there's a missing piece to the cosmic puzzle.
That's a really astute observation. And what's truly fascinating here is how this theory tackles those frustrations head on. Traditional approaches, whether they rely on axiomatic assumptions where we just sort of accept certain truths without proof, like postulates, or probabilistic interpretations, which often explain away quantum weirdness with mere chances, God plays dice, or even highly structural abstractions, they've just proven insufficient for a truly unified framework. They haven't bridged those gaps. And these aren't just minor glitches or mathematical curiosities. These paradoxes are profound indicators, really, of a missing foundational principle, something fundamental about reality that our current models simply aren't capturing. They're the cracks in our understanding that point to a deeper, maybe more elegant truth. They suggest that our current mathematical and physical language might not be speaking the universe's, its native tongue.
And here's where it gets really interesting and, quite frankly, mind-bending. Our source material indicates that the entire inquiry, this audacious new theory, actually began with a deep dive into a seemingly simple yet notoriously problematic mathematical expression, 0, 0, 0 to the 0th power. For most of us, we probably learned this in math class as being undefined or maybe indeterminate. It's a kind of mathematical black hole where the rules just seem to break down.
Precisely. And that's the crux. The assertion here that 0, 0, 0 is 1 isn't merely a trivial convention or, a clever proof within an existing mathematical system designed just to make the math tidier. Instead, in this new framework, it's proposed as a profound ontological insight, meaning an insight into the very nature of being and reality itself. It's put forward as a foundational axiom of what they call coherence invariance. Think of it not just as a mathematical statement, but as the self-generating principle, the very seed from which all mathematical and physical reality can be coherently constructed. Now, this is a direct challenge to that centuries-old philosophical debate. Is mathematics discovered, like Plato thought, these ideal forms existing somewhere, or is it invented by humans, like the formalists argue? This new view suggests it actually self-manifests through coherence principles. Mathematics, in this profound sense, begins not with arbitrary axioms of 0 or 1, but with an inherent principle of coherence. It's like the universe revealing its own consistent logic from the ground up.
Okay, so if 0001 isn't just a math trick, but this foundational axiom, this generative seed, what's the core shift in thinking that the UCTE proposes about the very logic of existence? You mentioned coherence as central. Can you help us really grasp what that means in this context, especially when contrasted with, say, randomness or entropy, which usually dominate these discussions?
This is truly the philosophical heart of the UCTE. It synthesizes the idea that coherence, which you can think of as inherent alignment, consistency, and harmonic interconnectedness, is the underlying generative logic of reality. This is a direct and radical contrast to prevailing scientific views that often emphasize randomness as the fundamental driver, or entropy, which points towards increasing disorder as the ultimate destiny of the universe. Instead, this theory posits that a principle called coherent selection is the primary driver. What does that mean? Well, it means that physical and mathematical structures emerge and stabilize, not through chaotic processes, but through the conservation and stabilization of coherence across all transformations. Imagine it like this. Coherence is never truly lost. It's simply redistributed or expressed in new forms, always maintaining fundamental consistency throughout all emergent phenomena. It's like the universe has an innate drive towards harmony and order, rather than just dissolving into chaos, a sort of self-organizing principle based on consistency.
That's a fundamentally different worldview. A universe driven by coherence, by inherent consistency and alignment, feels almost purposeful in a way, though maybe not consciously so. So how does this core axiom of 000 and the overarching principle of coherent selection actually extend across all these different scientific domains? It sounds like the ultimate grand unified theory, but with this very unique coherence-based twist. How does it knit everything together?
Indeed, the UCTE aims for a truly comprehensive unification, bridging fields that often seem quite disparate. Let's just sketch out its scope. In mathematics itself, the theory proposes that coherence isn't just a desired outcome, like elegance. It's the actual mechanism that stabilizes mathematical structures. It resolves those previously undefined cases we mentioned, like 0, and inherently ensures logical consistency from the ground up. When we move to quantum mechanics, the perplexing observer function, the idea that observation classes a quantum state, is radically redefined. It's no longer seen as a passive act that somehow breaks symmetry randomly. Instead, the observer acts as a dynamic coherence modulator. So the observer doesn't collapse a state randomly, or the interaction really, facilitates a coherent selection from a multitude of possibilities, kind of like tuning a radio to a specific coherent frequency.
Your coherence modulator. That's a fascinating image. Okay, what about other areas?
Right. For field theories, which describe the fundamental forces like electromagnetism or gravity, those underlying gauge symmetries, the mathematical symmetries that underpin interactions, are seen to emerge from something deeper called asymmetrical hypersymmetry. This suggests that fundamental forces are linked via a process called coherence reduction, hinting at a deeper, unified origin for all forces, stemming from a primary coherence. In cosmology, the UCTE offers intriguing hypotheses for some of the biggest cosmic mysteries out there. Phenomena like dark energy, which is accelerating the universe's expansion, and dark matter, providing that extra gravitational pull we observe, are proposed to arise from coherence-selected vacuum fluctuations, and maybe even neutrino condensates. This hints at a universe where even the empty vacuum is teeming with structured coherence. And even in cutting-edge fields like AI and computation, the UCTE suggests revolutionary approaches. It proposes things like coherence neural networks and quantum AI architectures that operate on the principle of coherence conservation. Imagine AI systems that inherently prioritize logical consistency and optimal alignment in their decision-making, making them potentially more robust and, coherent.
Wow. Okay, so the reach is enormous.
Exactly. The overarching aim here is truly ambitious: to unify both abstract mathematical realities and the emergent physical realities we observe, all through a meticulously layered architecture. It progresses, as we'll explore, from the Omnilectic to the Hololectic, then Relational, and finally Derived. Each layer critically builds upon and refines the coherence of the last, showing how fundamental harmony differentiates into the complex, structured universe we inhabit. #tag resolving mathematical mysteries with coherence.
This sounds incredibly ambitious, particularly when you talk about resolving long-standing issues in mathematics itself. You mentioned those undefined cases in classical algebra that give students nightmares, right? Things like 0 or dividing by 0, 0, 0, 0. In classical math, these are just blank spots, points where our system seems to break down. How does coherence theory actually fix these, making them meaningful instead of just undefined?
It's a really profound conceptual shift. moving from an idea of mathematical breakdown or discontinuity to one of inherent continuity instability. Classical mathematics considers 0, 0 undefined or indeterminate, largely because applying standard exponent rules directly can lead to contradictions or involve division by 0, 0, 0, 0, creating a fundamental discontinuity. It's a sticking point. But coherence mathematics, as we discussed, boldly defines 0, 0, 0 equals 1. And crucially, this isn't an arbitrary choice or just a convenient workaround to patch a hole. It's deeply justified by several rigorous arguments that support its inherent coherent nature.
Okay, so what are those justifications? Why one specifically?
Well, first, consider the limit interpretation from calculus. If you look at the function a raised to the power of a po, so a fo, and you let a approach to 0 from the positive side, meaning you get infinitesimally close to 0, but never quite reach the limit of a city, actually evaluates to exactly 1. This is a well-established result. So this definition 0, 0, 0, 1 isn't pulled out of thin air. It's the natural continuous limit of that function as it approaches this most fundamental point.
Right, I remember that from calculus. Okay, what else?
Secondly, there's a powerful combinatorial argument. Combinatorics is the branch of math dealing with counting arrangements and possibilities. The number of ways to choose 0 elements from a set of 0 elements is exactly 1. Think about it simply. If you have an empty box and your task is to choose nothing from it, there's only one way to succeed in that task: by doing nothing. This empty mapping represents a unique, singular, and well-defined state. It's not ambiguity, it's singularity.
The empty mapping. Okay, that makes sense too. And the third point.
And most critically, underpinning it all, is the coherence-preserving principle itself. The UCTE asserts that mathematical structures, especially at their most fundamental levels, should not break coherence. They shouldn't have these arbitrary gaps or points of failure. Defining 0, 0, 0, 1 ensures this foundational integrity and maintains a continuous flow of logic. It's like discovering that a hidden gear in a complex clockwork mechanism, previously thought to be broken or missing, actually completes the system perfectly when it's precisely defined as 1. It makes the whole machine work smoothly.
That makes incredible sense. It's like finding the missing piece that makes the entire mathematical puzzle continuous and consistent at its origin. Does this logic extend to other traditionally indeterminate forms as well, like 0, 0 error, or perhaps infinity, infinity? These are common stumbling blocks in math and physics.
Absolutely. The principle of coherence provides a consistent way to handle these as well, moving beyond simple undefinedness. Take 0, 0. In classical mathematics, it's undefined because it could represent many different values depending on the context. Think of two infinitesimally small numbers approaching 0 at different rates. But in coherence theory, division by 0, particularly 0, 0, results in what's called a coherent equilibrium state, not just undefinedness. It stabilizes at an invariant quantity, often related back to that foundational 1. Imagine two waves perfectly canceling each other out. They don't vanish into ambiguity. They reach a stable, 0 amplitude state, a point of equilibrium.
Okay, so instead of a breakdown, it's a stable balance point. What about infinities?
Similarly, infinity is traditionally undefined because infinity isn't a fixed number. Its value depends entirely on how you approach it. However, coherence mathematics treats infinities not as points, but as coherence gradients. Think of them as flows or potentials rather than static quantities. In this view, infinity represents the interaction of these gradients, which then stabilize at coherence invariance. It's like two immense opposing forces pushing against each other, eventually finding a stable, balanced point or a net result, rather than just resulting in an unpredictable, undefined struggle. Even 0 infinity, which is normally undefined, is seen to converge to a specific limit governed by coherence selection, provided coherence is conserved in the process. The core point, really, across all these cases is that coherence mathematics smooths out these mathematical discontinuities. It does this by ensuring coherence stabilization, making the entire mathematical landscape continuous, consistent, and fundamentally coherent at all levels, essentially eliminating these conceptual voids or breakdowns.
That's a fascinating way to look at it, shifting from undefined breaks to coherence equilibrium or stabilized gradients. It suggests a universe that inherently seeks balance and consistency, even at these extreme mathematical limits. Now, what about those really deep historical paradoxes in set theory, the ones that stumped mathematicians like Russell and Frege for over a century? Specifically, the empty set. Is ye something or is it nothing? If the number 0 is considered a member of a set, how can that set truly be empty? These seemingly simple questions led to profound philosophical and logical conundrums.
Yes, exactly. Set theory has indeed struggled with self-referential issues like Russell's paradox, the set of all sets that do not contain themselves, and this very paradox of the empty set. If zero is an element, a thing, how can a set containing only zero be truly empty? It seems to introduce a non-zero structure, a something, within what is supposed to represent pure nothingness. Our foundational axiom 0001 provides a truly elegant and profound resolution here, according to this theory. In this framework, zero is not merely emptiness or absolute void. It's redefined as a potential coherence generator. It's not the absence of something, but the potential for something to coherently emerge. It's the ultimate ground state.
A potential coherence generator. Okay, so how does that apply to the empty set itself?
So the empty set, denoted mel, is not treated as purely void or simple absence. Instead, it's defined such that its coherence value, let's write it as C equals 1. This C here signifies coherence. This means the empty set is not just an absence, it's a generative state, a singular point of unity and potential from which all mathematical structure can coherently unfold. Think of it as the ultimate seed, containing the potential blueprint for everything that can coherently emerge, all starting from this state of perfect, singular coherence represented by 1.
That's a huge shift in perspective on nothingness.
It is. And this redefinition is critical because it allows for the immediate and crucially coherent emergence of complex mathematical structures directly from this foundational point. For instance, consider exponentiation based on this axiom, 0, 0, n equals 1. This consistently preserves invariance, meaning 1 raised to any power remains 1, maintaining fundamental consistency across scales. It doesn't break down. Look at factorials. n01 for any non-zero n is a standard definition. Defining 0, 0, 0 as 1 naturally leads to 0 point also being 1. This provides a seamless and coherent foundation for combinatorial definitions and set relationships. And remember the limit lim x equals 1. This provides a natural and consistent bridge to infinitesimal calculus, ensuring a smooth transition between discrete concepts like zero and continuous realms, avoiding abrupt breaks. This is a crucial distinction from traditional mathematical ontologies. Platonism suggests math exists as ideal forms independent of us. Formalism views math as just a game of symbols based on arbitrary axioms we choose. Nominalism says math is just useful human linguistic constructs. But this new framework allows mathematics to emerge systematically, organically, and without internal conflict, always rooted in this self-generating principle of coherence, 001. It addresses the ontological status of mathematics itself, moving beyond it being merely invented or discovered to being fundamentally self-manifesting through its own internal coherence. It suggests a universe that builds its own consistent rulebook from the most fundamental potential imaginable.
That's a truly elegant way to potentially resolve some very deep mathematical and philosophical puzzles. So we've talked about this core axiom, 001, and its profound implications for basic math and ontology. Now let's zoom out. Let's explore how this incredible idea of coherence manifests in the very fabric of reality itself, across all scales of existence. Our sources talk about a layered framework providing a clear hierarchical structure, from universal invariance down to the applied structures we observe every day. It even mirrors something called the big emergence framework in physics, which looks at how complexity arises. This is the unified coherence theory of everything, or UCTE in detail. How does this layered universe unfold? Where do we start?
Exactly. The UCTE organizes all of mathematical and physical reality into 4 interconnected, progressively emergent layers. Think of it like zooming in on reality, level by level. These layers are Omnilectic, Hololectic, Relational, and Derived mathematics. Each layer reflects a progressive symmetry reduction and emergence, showing how fundamental, unified coherence differentiates and manifests at increasingly complex and concrete levels of reality. It's like a cosmic unfolding, where the pure potential of one layer coherently gives rise to the structured forms of the next without losing that initial harmony. Let's start at the absolute top, the deepest level. Omnilectic mathematics. This is the foundational layer, representing the most invariant, unified principles of hypersymmetry and absolute coherence. Imagine it as the deepest substrate of reality, existing as the universal invariant mathematical framework within hyperspace, independent of any specific universe and preceding what we call the big emergence or the Big Bang. It's the pre-existent template for all coherent reality, the ultimate source code, if you like.
Hyperspace, pre-Big Bang. Okay, this is deeply fundamental. What are its key characteristics?
Its core properties are crucial to understand its role. First, universality. It encodes all possible mathematical structures within an undifferentiated state. It's like a cosmic genetic code containing the potential for every mathematical form imaginable before any are actually realized. Second, invariance. It's governed by immutable principles, unchanging rules like universal conservation laws, energy, momentum, etc., and fundamental symmetry operators. These are the unbreakable laws that persist throughout all subsequent transformations and layers of reality. And critically, absolute coherence. This layer is characterized by a perfect, primordial alignment of all components, ensuring no internal contradictions. There's an ultimate, unblemished harmony at this pre-emergent level. It's pure, undifferentiated consistency.
So this omnilectic layer sounds almost like pure unmanifested potential, the cosmic blueprint before anything physical actually exists. It's hard to picture. Can you give us a sense of what kind of mathematical examples might live in this extremely abstract realm? What represents this absolute coherence?
Absolutely. While deeply abstract, we can conceptualize these through highly fundamental mathematical structures that underpin physics. Think of symmetry groups like SUN, SON, and U1. These aren't just arbitrary symbols. They represent the deepest, most fundamental rules or symmetries that govern how things can behave at these absolute levels. For example, U1 symmetry underlies the electromagnetic force, while SU2 relates to the weak nuclear force, and SU3 governs the strong nuclear force. In this framework, these groups describe invariance under transformations, acting as the bedrock for gauge theories and quantum mechanics even before particles or forces manifest in our universe. They are the potential for those forces.
Okay, so the potential for forces. What else?
Then there are the universal constants, things we measure like c, the speed of light, h, Planck's constant, the quantum of action, and g, the gravitational constant. In this framework, they're not merely measured values that happen to be what they are. They're modeled as invariant quantities that originate directly from this omnilectic layer, representing inherent unchanging relationships within the universal blueprint itself. There are constraints imposed by the absolute coherence. And finally, structures like Lie algebras, such as SU2 or SU3, which generate continuous symmetries, encode these symmetry operators and their potential for transformation prior to their actual manifestation in the universe.
Yeah.
They are the mathematical engines of symmetry, existing in a state of pure, unexpressed potential.
That paints a clearer picture, connecting it to things fundamental to physics. What's the philosophical takeaway from this layer?
Philosophically, this layer powerfully reflects the concept of undifferentiated hypersymmetry, a state of perfect symmetry and potential thought to exist before the Big Bang, or what this theory calls the big emergence. It's the pre-emergent reality, strongly suggesting that mathematics and physics aren't human constructs or accidental byproducts of our specific universe. Rather, they arise organically from an absolute invariant foundation. This Omnilectic layer provides the ultimate context for understanding existence as a mathematical and physical continuum. So in this profound view, mathematics isn't invented by us, nor is it merely discovered as a pre-existing Platonic form. It is quite literally revealed as symmetry reduces, emerging step by step from this fundamental source of coherence.
That's a truly mind-bending concept. Mathematics revealing itself as symmetry reduces, like uncovering a statue from a block of marble. It makes perfect sense that something so fundamental would exist before the universe as we know it. Okay? So, from this absolute pre-emergent layer of omnilectic mathematics, this realm of pure potential and symmetry, how do these invariant principles actually start to manifest? How do they give rise to the continuous forces and fields that we perceive as the fabric of reality? What's the next step in this cosmic progression as the universe begins to take on actual form?
That leads us directly to the second layer, hololectic mathematics. This is the critical layer where those unified abstract invariants from the omnilectic level begin to manifest as continuous field-like structures. Think of it as the conduit, the crucial bridge between that absolute unmanifested coherence and the emergent relational systems that follow. It's where the pure blueprint starts to take on a vast, continuous, but still unified expression.
Hololectic, like holistic and dialectic. Okay. What are its defining features?
Key properties of hololectic mathematics include, first, continuity. It describes systems as smooth, unbroken structures, like pervasive fields or what mathematicians call differentiable manifolds. These encode relational dynamics as differentiable holistic entities, meaning they can be analyzed using calculus and represent entire systems smoothly. Then there's holism. This layer inherently models entire systems, focusing on the intricate interplay of components within a coherent framework, where, much like a hologram or a living organism, the whole is greater than the sum of its parts. The interconnectedness is key. And critically, the preservation of coherence from the omnilectic layer is fully maintained here. That fundamental harmony isn't lost, it's simply expressed differently through these continuous fields, ensuring consistency as reality takes on a more expansive form.
That's a great way to put it, the blueprint becoming a vast, continuous fabric, still whole but now extended. Can you give us some concrete mathematical examples of these continuous fields and structures? How do they relate to the physical world we actually study and observe?
Certainly. When we talk about hololectic mathematics, think of foundational concepts in physics like tensor fields. A prime example is the Riemann curvature tensor, Reichel, in general relativity. This mathematical object precisely describes the curvature of spacetime as a continuous field. It tells us how mass and energy warp the fabric of the universe, which we experience as gravity. That's a hololectic description. We also have differentiable manifolds. These are essentially smooth, continuous spaces where calculus can be applied consistently. Our familiar four-dimensional spacetime, often described by a manifold M with its metric guide defining distances, is a perfect example of a hololectic structure. It's the continuous stage upon which all physical events unfold.
Okay, space-time itself. What else?
Gauge fields are another key example. These fields are central to quantum field theory. They encode symmetry transformations and mediate the fundamental interactions. The electromagnetic field, A, which governs light, electricity, and magnetism, is a fundamental gauge field. It's a continuous entity that permeates space and mediates the electromagnetic force. Then there are Hilbert spaces. These are typically infinite-dimensional vector spaces that are absolutely fundamental to quantum mechanics. The state of a quantum system, like a particle's wave function, often living in a space like L2R, exists within a Hilbert space. These spaces represent the complete set of possibilities for a quantum system, continuously distributed before any measurement. And finally, differential operators which act on these fields to describe their dynamics, how they change over time and space. Operators like the Laplacian or the Dirac operator are used in fundamental equations like the Klein-Gordon equation plus m to a 0 or the Dirac equation, which describe the behavior of various types of fields.
So this layer basically covers all the fundamental fields of physics.
Pretty much, yes. Philosophically, this hololectic layer beautifully corresponds to the pervasive, field-like structures that govern all fundamental physical interactions: electromagnetic fields, gravitational fields, the space-time curvature, the fields associated with the nuclear forces, and quantum fields in general. It models the universe not as a collection of isolated particles, but as a continuous, interconnected whole. It truly serves as the essential conduit between those absolute, invariant principles of omnilectic mathematics and the dynamic, observable systems that emerge in the next layers. This is the pivotal moment, you could say, when universal coherence begins to differentiate and flow into the continuous forms that govern cosmic dynamics, setting the stage for interaction.
It's incredible how each layer builds upon the last, becoming progressively more defined, yet still so abstract and continuous at this hololectic stage. It's like the smooth surface of an ocean. So from these continuous holistic fields of hololectic mathematics, this background fabric of reality, how do we get to the actual interactions, the waves rippling on that ocean surface, the connections, the dynamic processes that truly define the world we perceive? How do those smooth fields differentiate further to give us the vibrant, interactive universe? Where do the dynamics come in?
That's precisely where the third layer, relational mathematics, comes into play. This layer represents a critical step in the cosmic unfolding, shifting the focus to profoundly emphasize interactions, transformations, and connections between entities within a coherent system. It's where the continuous fields begin to express themselves in dynamic relationships, like waves forming on that ocean.
Interactions, transformations, connections. Okay, what are its specific properties?
Its core properties are all about this dynamic interplay. First, localized relationality. The focus shifts from the entire continuous field, like the whole ocean, to specific relationships between components, like individual waves interacting. Think of mappings, geometrical connections, or correlations. It's about how things connect and influence each other, emphasizing those relationships over the individual entities themselves in isolation. Second, dynamic behavior. This layer explicitly describes oscillatory, periodic, and resonant behaviors. These include mathematical ideas like periodic functions, sines, cosines, harmonic relationships, and wave phenomena. It's important to note that these don't strictly require physical oscillations yet, but rather describe the mathematical patterns of dynamic interplay and resonance inherent in the fields. And finally, interconnectivity. This property ensures that coherence is maintained across systems even as they interact. It describes how relational dynamics preserve or propagate these connections, ensuring the system stays harmonious and consistent even as its parts interact dynamically. It's about how the harmony persists through change.
Okay, so this is where the action really starts. Can you give us some tangible mathematical examples here? How do these ideas translate into the kind of math that describes waves, relationships, or quantum phenomena?
Absolutely. One of the best examples is Fourier analysis. This incredibly powerful mathematical tool takes complex functions or signals and decomposes them into simpler sinusoidal components, like writing fx e to x. It's essentially how a continuous hololectic system, like a complex electromagnetic field, reveals its underlying dynamic oscillatory parts like individual waves of light with specific frequencies and amplitudes. It bridges the holistic view to the relational components.
Right, breaking down complexity into simpler waves. Makes sense.
Then we have explicit wave equations, like the classic wave equation 2 Uriel 2 C2 Uriel 2, or the Schrödinger equation in quantum mechanics. These are partial differential equations that directly encode dynamic interactions and propagation. They describe how disturbances, whether sound waves, light waves, or quantum probability waves, move through a medium or field, governing their relational behavior over time and space. Graph theory is another compelling example in this layer. It models interconnected systems, things like neural networks, social networks, or even lattice structures of materials through the relationships between vertices, nodes, and edges, connections. Often represented by an adjacency matrix A, it's a mathematical language purely focused on describing networks and their dynamic flow of information or influence.
So networks fit here too. Interesting.
Yes, and even abstract fields like topology and homotopy, which deal with properties and transformations that preserve connectivity, like how many holes an object has, fall into this layer. Concepts like the fundamental group 1M, which describes the different kinds of loops you can draw in a manifold without breaking them, reveal deep relational structures that remain invariant under continuous deformation. They capture the essence of connection. And crucially, quantum wave functions, the very heart of quantum mechanics, are prime examples of relational mathematics. These are solutions to the Schrödinger equation, describing probability amplitudes and how particles interact. They inherently embody concepts like superposition, C11 plus C22, where a particle exists in a relationship between multiple states, and entanglement, which is a purely relational phenomenon. The state of one particle is intrinsically, instantaneously linked to the state of another, no matter the distance.
Entanglement is definitely relational.
Absolutely. And lastly, even classical mechanics has a relational formulation, Lagrangian mechanics, where the dynamics of a system are derived relationally by finding the path that minimizes a quantity called the action, SC and D, where LTV is the difference between kinetic and potential energy. It derives motion from principles of interaction and energy relationships. The transitions from Hololectic to relational mathematics are fascinating and really help illustrate this progressive emergence of structure. For example, a continuous gauge field X from the Hololectic layer, think of the universal electromagnetic potential field, doesn't just sit there. It dynamically breaks into localized wave functions that describe individual photons or electrons, thereby encoding particle-wave duality, a key relational concept. Maxwell's equations, Wade-Shea, which describe the hololectic electromagnetic field, directly give rise to electromagnetic waves, Roshans 1C2 areas of 0, 0, which are clearly relational phenomena propagating disturbances. Or consider spacetime. A differentiable manifold M with its metric G, a hololectic description, defines relational connections like geodesics, d2x2 plus omin depicts d2x up 0, which are the specific paths objects follow due to the gravitational relationship defined by the manifold's curvature. Even in abstract Hilbert space, hololectic, operators like the Hamiltonian produce relational dynamics like time evolution, IGOJ, describing how quantum states evolve through their relationships with energy and potential.
Okay, so the continuous gives rise to the dynamic interactions. What's the deeper meaning here?
Philosophically, this relational layer reflects the universe's innate ability to differentiate that initial holistic coherence into interactive and localized systems. It strongly suggests that, quote, reality is not composed of isolated entities, but fundamentally of the relationships and interactions between them. The connections are primary. And concepts like resonance, which is core to wave theory in music, become a key principle here, as oscillatory behaviors naturally emerge from the harmonic properties inherent in the underlying holectic fields. It's where the continuous fabric of reality starts to ripple, vibrate, and communicate, creating the dynamic interplay we observe all around us.
This is truly mind-bending, seeing how continuity gives way to interactions and waves, bringing us much closer now to the universe we actually experience. But our perceived reality is also distinctly full of discrete things, individual particles like electrons and photons, distinct measurements that give specific numbers, countable objects like atoms or stars, It's not all just waves and relationships. So how does all of this, the omnilectic potential, the hololectic fields, the relational interactions, how does it finally lead to the discrete, quantized, and symbolic layer that we experience every day? What's the final tangible step in this grand unfolding from pure coherence?
That final step in the unfolding of coherence brings us to the fourth layer, derived mathematics. This is the layer where those localized relational dynamics we just discussed are quantized, symbolized, or discretized into finite, observable forms. It's the final step in the symmetry reduction process, where the continuous and relational coherence, originating all the way back from the omnilectic layer, finally resolves into observable, distinct units. This is the layer that most closely matches the fabric of our everyday experience and scientific measurement.
Okay, derived. So this is where things become countable, measurable. What defines this layer?
Its core properties are quite distinct from the previous layers, focusing on discrete structures. First, quantization. This is the crucial reduction of relational dynamics, like waves, into discrete countable entities. Think of fundamental particles, integers, or the specific energy eigenvalues measured in quantum systems. Even here, though, and this is critical, the underlying coherence and symmetry originating from the deeper layers are rigorously preserved within these discrete frameworks. Quantization isn't random, it follows coherent rules. Second, symbolism and representation. This is where systems are encoded in abstract symbolic forms that allow for manipulation and computation. Think of algebraic equations, matrices representing transformations, or symbolic logic. This is where we get the tools for formal reasoning calculation. Underpinning it all is discrete coherence. Even in this world of discreteness and symbols, the underlying coherence from the relational and hololectic layers is retained. The harmony is still there, just expressed in distinct notes rather than a continuous tone. And ultimately, this layer holds immense practical utility, forming the basis for all computation, measurement, symbolic reasoning, and the technologies we build upon them.
So this is where the abstract concepts become concrete tools and measurable quantities, where we can finally count things and write down equations. Can you give us some specific mathematical examples of this derived layer? How does it lead directly to what we physically measure or compute?
Certainly, some of the most familiar mathematical tools reside squarely in this layer. Number theory and modular arithmetic, for instance, are quintessential derived mathematics. The study of integers, their divisors, prime numbers, and congruences like AOB, mod n, which is the backbone of modern cryptography, exemplifies discrete mathematical structures derived from more fundamental principles. Eigenvalues and eigenvectors are absolutely central. These are the discrete, specific solutions that arise when linear transformations, like quantum operators, act on systems, HNFA, C, E, N, A, and A. They are fundamental to quantum mechanics, describing the discrete specific energy levels of an atom, like the hydrogen spectrum, N = 13.6 eV N2, or the distinct spin states a particle can occupy when measured. Measurement yields discrete results.
Eigenvalues are definitely about getting specific numbers out. Got it.
Exactly. Then there's combinatorics, the study of discrete arrangements, selections, and counting things, permutations, P(n)(10k) and Cambay. This also falls squarely into derived mathematics, dealing with finite sets and discrete possibilities. We also find fundamental algebraic structures here, like finite groups, rings, and fields, such as ZPZ, the integers modulo of prime P, which provide the framework for abstract algebra and have applications from coding theory to particle physics. Finite graphs and matrices are used everywhere to discretize relational structures for analysis. An adjacency matrix A turns a network diagram, relational, into a computable object, derived for analyzing connectivity or running algorithms. The discrete Fourier transform, DFT, is a perfect practical application. It takes finite discrete data points, like a digital audio sample, and converts them into discrete frequency components, xk = SMAE I2k and n. It essentially quantizes the continuous relationships of the Fourier transform, relational for computational use, underpinning digital signal processing. Even things like cellular automata, like Conway's Game of Life, which use simple rules on a discrete grid to generate complex patterns that approximate continuous dynamical systems, belong to this derived computational layer.
Okay, so it covers everything from basic numbers to quantum measurements to computer algorithms. How does the transition work? How do we get from waves to numbers?
The transitions from relational to derived are crucial and beautifully illustrate the culmination of this unfolding process, where continuous or relational ideas become discrete tools or results. For instance, a continuous function fx from the relational layer, like a complex sound wave, undergoes a Fourier transform. But for practical use on a computer, it becomes its discrete frequency components, xk, via the DFT, derived. This is essential for digital signal processing, image compression, and more. Or think of a quantum wave function in Relational, which represents a particle's potential state spread out in space. During a measurement, it collapses, or perhaps is coherently selected, into a single discrete eigenstate Na with a specific eigenvalue like energy or position derived. This is the foundation of atomic spectra and quantum computing measurements. Topological properties, relational, like the way electrons flow around defects in a material, can yield discrete quantized invariants like Chern numbers in phase E2AC and things like topological insulators, derived. These discrete numbers dictate unique, robust electrical properties, leading to novel materials. A graph G, VE, relational, simply describing connections, becomes a discrete adjacency matrix AJ, derived, for efficient network analysis, allowing algorithms to calculate shortest paths or community structures. Even continuous wave equations, relational, are often solved numerically by discretizing them on a lattice, turning the PDE into a set of algebraic equations. Uni plus 1 fields ever equals to uni plus 1, 2, 2, uni 1, and 2, solvable by a computer derived. This is how we simulate everything from weather patterns to quantum fields.
That really connects the dots, showing how the abstract becomes computable and measurable. What's the philosophical insight here?
Philosophically, this derived layer represents the culmination of the symmetry reduction process, where the continuous and relational coherence flowing down from the deeper layers finally resolves into the distinct, measurable units we perceive and manipulate. It directly represents the foundations of measurement, aligning perfectly with the inherently quantized nature of physical measurements. In our observable universe, we always measure discrete values. And fundamentally, it provides the practical utility for computation, symbolic reasoning, and technology, all deeply rooted in the underlying coherence established in the earlier, more abstract layers. It's where the abstract harmony of the universe crystallizes into the concrete, countable, and computationally accessible reality we experience.
Okay, this UCTE framework, with its layers from Omnilectic potential down to derived measurements, sounds like it's completely redefining some of the most fundamental areas of physics. Let's really dive into how it reinterprets quantum mechanics specifically. This is where so many of the paradoxes we started with reside: superposition, collapse, entanglement. It sounds like UCTE offers a fundamentally different way to understand them, maybe resolving some of the weirdness.
It truly is a profound reframing of quantum reality, aiming to replace mystery with mechanism, specifically a coherence mechanism. In the UCTE, concepts like superposition, where a quantum particle seems to exist in multiple states simultaneously before measurement, are not just seen as abstract probability amplitudes residing in Hilbert space, as in the standard Copenhagen interpretation. Instead, wave functions are treated as tangible, coherence-preserving structures. They represent a real, physically coherent state distributed across possibilities. This means the act of quantum collapse, or wave function collapse, isn't viewed as a random, unpredictable dice roll, where possibilities suddenly solidify into one reality upon measurement. That's always been a sticking point. Rather, it's interpreted as a selection effect from hypersymmetric coherent states. It's seen as a coherent, possibly deterministic process that selects the most harmonious and consistent outcome from the available potential states, rather than a purely random symmetry breaking. Think of it as reality coherently choosing its most stable path, much like water naturally flows downhill to the lowest energy state, rather than randomly jumping around.
So the selection isn't random. That's a huge departure.
That's the proposal, yes. It shifts the foundation away from inherent randomness. And for entanglement, that spooky action at a distance where two particles become mysteriously linked, regardless of separation, its stability isn't just a correlation. It's governed by coherence conservation across spatially separated systems. This implies an active maintained coherence linking the particles. The theory even predicts the possibility of new potential quantum states beyond classical entanglement, suggesting that our current understanding of entanglement might be incomplete. The source material apparently includes theoretical plots showing stable phase-locked entangled states that could be more robust or complex than what standard quantum mechanics might predict. Even the quantum vacuum states, the seemingly empty space that quantum field theory tells us is actually teeming with virtual particles popping in and out of existence, are redefined. They're seen as a coherence background state. This means vacuum fluctuations are not just random fizzing in the void, but potentially structured manifestations of coherence interactions rather than purely random fluctuations. They are subtle expressions of the underlying coherence of spacetime itself.
Wow. And does this framework offer a way to derive the core equations of quantum mechanics, like Schrödinger's equation?
Remarkably, yes. The source material claims that the Schrödinger equation itself, the central dynamical equation of non-relativistic quantum mechanics, can be derived within this framework, tracing back conceptually to the 001 axiom and the principle of coherence. It's expressed as a coherence-driven equation, schematically something like IRL C, task 2 and 2 plus V. The key here is the C, representing the coherence function, which ensures that all allowed quantum states and their evolution are coherent selected and maintain consistency with the underlying layers. This implies a universe where quantum behavior is not inherently probabilistic at its deepest core, but rather follows a deeper deterministic coherent logic. It aims to shift quantum mechanics from primarily a statistical description of uncertainty to a more precise description of how coherence manifests and evolves at the smallest scales.
That's a monumental reinterpretation of quantum reality, potentially removing the need for pure randomness. Now let's try and bridge this to the largest scales. How does this coherence framework unify with Einstein's general relativity, which describes gravity and the structure of spacetime? What does coherence-based relativity, or CBR, look like in this picture?
In coherence-based relativity, CBR, the very fabric of spacetime is fundamentally redefined, much like the quantum state was. It's not seen as a fixed background stage, nor merely a geometric construct that passively gets warped by mass. Instead, spacetime itself is defined as a coherence field, perhaps represented mathematically as ds2 equals c, dx2 plus di2 plus dz2 ctt2, where c again is the coherence function. This implies that spacetime doesn't just exist. It emerges dynamically from the flow and interaction of coherence. It's constantly adapting and organizing itself based on the coherent interactions happening within it. Think of it as a dynamic, self-organizing medium rather than a static stage.
So spacetime itself is an emergent property of coherence. How does that enter gravity and Einstein's equations?
Exactly. The Einstein field equations, EFE, GIM on 8GC14, which masterfully describe how mass and energy two-curve spacetime geometry are also profoundly re-envisioned. Gravity, in this theory, is not merely a consequence of geometry. It's treated as an effect of the coherence function itself. The EFE might be rewritten schematically as GIN C C48 This implies that spacetime curvature, which we experience as the force of gravity, is not an independent phenomenon, but an emergent result of coherence flow. Gravitational fields are simply manifestations of how coherence is distributed and flowing through the universe, influenced by mass and energy.
Okay, so gravity is coherence flow. What about things like time dilation or length contraction?
Even familiar relativistic effects like time dilation are given a new interpretation within CBR. It's not simply an effect of relative velocity or gravitational potential changing the rate of time. Instead, it's viewed as a coherence shift, perhaps described by an equation like T, where CV is a coherence factor dependent on velocity. This means that all relativistic effects, from time slowing down for fast-moving objects to the bending of starlight around massive objects, are seen fundamentally as coherence-induced transitions. The flow and distribution of coherence is being altered by relative motion or mass energy, leading to these observable changes in measured time and space, all while preserving the underlying coherence of physical laws. Now, moving from relativity to the entire cosmos, the UCTE connects coherence directly to the grandest phenomena in the universe. It proposes a coherence-based early universe emergence model, offering a potentially new narrative for how our cosmos began and evolved, rooted in these principles of unfolding coherence rather than just a chaotic Big Bang followed by inflation. For the enduring mystery of dark matter, that invisible stuff making up most of the universe's mass, the theory puts forward a fascinating specific hypothesis: a coherence-selected neutrino condensate. This suggests that neutrinos, those incredibly light and weakly interacting particles, could, under specific coherence conditions, perhaps present in the early universe or galactic halos, form large-scale condensates that collectively exert the gravitational effects we attribute to dark matter. It's a bold, potentially testable alternative to hypothetical new particles.
A neutrino condensate. Interesting. What about dark energy?
And the perplexing vacuum energy discrepancy, often called the worst prediction in physics, where theoretical calculations of the vacuum's energy density are astronomically larger, like 120 orders of magnitude, than what cosmology observes driving cosmic acceleration, dark energy, is proposed to be resolved within this framework via something termed hypergravity coherence. This introduces a new fundamental concept, hypergravity. This isn't just stronger gravity, it's described as a fundamental coherence field that potentially provides the missing link, unifying gravity with quantum fields and the other gauge interactions at a deeper level. It's conceived as the overarching coherence field that mediates all fundamental forces, ensuring their seamless interaction and potentially canceling out those huge vacuum energy contributions naturally, leaving just a small observed residue as dark energy.
Hypergravity, unifying all forces through coherence. That's the holy grail right there. This truly covers the gamut from the quantum realm to the vastness of the cosmos. But what about more practical, maybe even everyday applications, or at least applications closer to our current technological reach? How does this coherence theory translate into fields like artificial intelligence, information theory, and computation? Does it offer new tools or perspectives there?
The implications here are potentially profound and indeed highly practical, possibly revolutionizing areas, from how we design AI to how we build quantum computers. In AI decision-making, for instance, traditional AI often relies heavily on probability and statistical weighting, finding the most likely pattern or outcome based on data. Coherence-based AI, as envisioned in the UCTE, would operate differently. It would select decisions that maximize coherence across multiple input gradients, meaning it actively seeks the most harmonious, logically consistent, and globally optimal outcome, not just the statistically most probable one. This could potentially make AI more stable and resilient than standard probability-weighted systems, less prone to unexpected errors, logical contradictions, or getting stuck in suboptimal solutions. It would have an inherent drive towards consistency.
AI seeking coherence, that sounds almost like wisdom. What about the structure of AI?
Exactly. This leads directly to the concept of coherence neural networks, CNNs, note. This is distinct from convolutional neural networks, also called CNNs. These are envisioned as a next-generation AI architecture. Here, the neural nodes wouldn't just pass information signals based on weights. They would actively maintain coherence memory, meaning they'd retain information about the consistency and relationships between data points, preventing catastrophic forgetting and processing information holistically. More like how the human brain seems to work, by finding resonant patterns and connections, rather than just processing isolated data points linearly. For quantum AI, combining AI with quantum computing, the UCTE suggests optimizing AI behavior within quantum architectures using quantum coherence selection. This could be a pathway towards error-free quantum computing, potentially solving the pervasive problem of decoherence, where quantum states lose their coherence due to environmental noise that plagues current quantum systems. By actively selecting for and preserving coherence, UCTE might make quantum computers robust and practical.
Error-free quantum computing. That would be game-changing. What about information itself?
In information theory, the UCTE even redefines fundamental concepts like Shannon entropy. Entropy usually measures uncertainty or disorder. Here, it's potentially reframed in terms of coherence preservation, perhaps SIE C pi log C pi, where C pi is the coherence of a state pi. This suggests that even apparent disorder might be a complex but coherent state of information redistribution. Quantum information itself is viewed fundamentally as a coherence-preserving transformation, perhaps quantified as IQ/CH quantum, highlighting the inherent order and preserved consistency within quantum states and operations. This perspective even offers a potential resolution to the notorious black hole information paradox, the baffling question of whether information is truly destroyed when matter falls into a black hole, which would violate quantum mechanics. The UCTE resolves this by defining information fundamentally as coherence-preserved, actual, final, initial. This implies that black holes don't destroy information or coherence. They simply redistribute coherent states in a highly complex way, perhaps encoding it on the event horizon or in Hawking radiation, ensuring that no fundamental information is ever truly lost, just transformed. And this naturally leads to the technological possibility of coherence-preserving quantum circuits, designing quantum computing architectures from the ground up, based on principles that actively eliminate decoherence errors through coherence conservation, rather than just trying to correct errors after they happen.
This all sounds incredibly compelling, weaving together math, physics, cosmology, and even AI and information, offering potential solutions to some of the most persistent problems in modern science and technology. But, okay, as with any ambitious scientific theory, the ultimate test is, can we test it? Can we prove it wrong? What are the specific experimental and observational predictions of UCTE that could either provide strong evidence for it or potentially disprove its core claims? Where does the rubber meet the road?
That's the absolute critical question, yes. A theory is only as good as its testable predictions. And the UCTE framework, according to the source material, provides several clear pathways for empirical validation, moving it beyond just mathematical elegance or philosophical speculation. One key area is testing coherent selection in quantum systems. This isn't just theoretical, it suggests concrete experiments. For example, physicists could design and build new types of quantum gates or qubits based explicitly on UCTE principles, what might be called coherence-based quantum gates, and meticulously compare their performance, like error rates and coherence times, against traditional qubits that are highly susceptible to decoherence. If these coherence-based gates exhibit significantly lower error rates, maintain quantum states for much longer periods, or show evidence of the predicted selection effect instead of random collapse, that would constitute strong experimental evidence.
Okay, so lab tests on quantum devices. What about looking outwards to the cosmos?
Absolutely. There are coherence-based cosmological observations that could be made. This involves looking for specific, unique signatures predicted by the UCTE models for phenomena like dark matter and dark energy, or perhaps for evidence of the proposed hypergravity field. This can involve searching for subtle, predicted anisotropies or polarization patterns in the cosmic microwave background radiation that differ from standard lambda CDM cosmology predictions, or looking for unique gravitational lensing patterns around galaxies or clusters that might betray the presence of neutrino condensates or hypergravity effects. These would be distinct fingerprints of the theory. We could also focus on measuring coherence eigenvalues in particle physics. This means designing experiments, perhaps at high-energy particle colliders like the LHC or future machines, to actively seek specific, measurable properties related to coherent selection. This could potentially provide a new framework for predicting particle behaviors or interactions beyond the standard model, looking for deviations that align with coherence principles rather than just adding more epicycles or parameters. It's about finding new coherence-based quantum numbers or conservation laws.
So particle physics signatures too. Any direct technological implications that could be tested?
And of course, the technological implications themselves offer test beds. The theory hints, perhaps optimistically, at the potential for coherence-based energy extraction. While speculative, if the vacuum is indeed a coherence background state, could we devise ways to tap into that inherent coherence for clean, abundant energy? Proving or disproving such a radical possibility would certainly be a major test. The point is, the theory isn't designed to be purely abstract. It's intended to connect directly to the physical world through testable predictions, bridging the gap between its deep mathematical elegance and concrete empirical reality. It offers a new frontier for experimental physics to explore.
Now, for the intellectual heavy lifting, perhaps, and something that addresses a fundamental concern for any grand unifying theory, especially one that redefines mathematics itself. Any theory aiming to fundamentally reshape our understanding of math and physics has to contend with some of the deepest challenges in logic and the foundations of mathematics, namely Gödel's incompleteness theorems. These theorems, famously, suggest that any sufficiently complex formal system, like arithmetic, cannot prove all truths about itself without either being incomplete, meaning there are true statements within the system that it simply cannot prove, or inconsistent, meaning it can prove contradictory statements, like 1 to 0. It's a profound limit on self-contained, self-referential systems. How does this coherence framework, which seems to be building mathematics from its own 001 axiom address, or perhaps cleverly sidestep these potentially devastating pitfalls discovered by Gödel?
That's an absolutely critical point, and it's where the logical architecture of the UCTE really shows its sophistication, according to the proponents. The framework aims to sidestep Gödel's pitfalls precisely by not being a purely self-contained formal system in the traditional sense, which is the kind of system Gödel's theorems primarily apply to. Instead, it proposes an external axiomatic basis. Rather than trying to root mathematical truths entirely within a conventional formal system built upon itself, which would then be subject to Gödel's limitations on self-proof, it grounds them in the concept of hypersymmetry reduction, originating from that Omnilectic layer.
Okay, so it points outside itself for its foundation.
Exactly. Hypersymmetry, as we discussed in the Omnilectic layer, is conceived as existing outside or prior to the conventional formal system of mathematics, as we usually practice it. It serves as the metasystem, a higher-order reality or potentiality from which mathematics emerges coherently. This means that the foundational truths of the UCTE aren't attempting to prove themselves solely from within a closed loop, thereby aiming to avoid the direct self-referential paradoxes. This statement is false, that Gödel identified as leading to incompleteness or inconsistency. It's like a computer program whose fundamental operating system isn't written in its own code, but is installed from an external foundational source, ensuring its internal consistency by not relying entirely on itself for its own core definitions.
Interesting. And external grounding. Are there other ways it addresses Gödel?
Yes. Secondly, the UCTE incorporates dynamic emergence. By modeling the emergence of mathematics as a continuous layered process of symmetry reduction, the framework introduces a temporal and causal component. This means it avoids treating mathematics as a purely static, fixed, self-contained system, which is the context where Gödel's limitations most strongly apply. Instead of being just a fixed set of axioms and derivable theorems existing timelessly, mathematics is seen as a dynamic unfolding, an ongoing process of coherent manifestation through these layers. This dynamic, process-based perspective is crucial for potentially escaping the static limitations. And finally, related to this, there's a reliance on relational proof. Rather than attempting to establish the ontology through absolute, potentially self-referential statements that could lead to inconsistency, this system is complete and consistent, which Gödel showed is problematic. The UCTE approach uses the inherent relations and transformations within the hypersymmetry reduction process itself to demonstrate emergence. This relational process-based methodology aims to avoid the pitfalls of self-referential absolutes. The claim isn't, this system proves itself from within. The claim is more like, this system emerges consistently from a coherent, higher-level process, and that emergence itself guarantees its ongoing coherence.
That's a truly sophisticated way to reframe the challenge posed by Gödel, invoking an external metasystem, a dynamic process of emergence, and focusing on relational consistency rather than absolute self-proof. So if it's not relying on a traditional self-contained axiomatic system in the Gödelian sense, what mathematical framework does the UCTE utilize to provide its formal structure and proof? Our sources mention category theory, which for many listeners might sound even more abstract and intimidating than quantum field theory or general relativity. Can you demystify that a bit?
You're right, category theory can sound daunting, but it's actually the ideal formalism for this kind of framework, precisely because it's designed to talk about structures and relationships in a very general way. It fundamentally emphasizes morphisms, which are structure-preserving transformations or relationships between objects, rather than focusing solely on the objects themselves, like sets and elements in traditional math. This provides a powerful, unifying language that is perfect for describing how different mathematical structures or layers of reality interact, transform into one another, and maintain consistency. It's inherently relational, which aligns perfectly with the UCTE's core emphasis on coherence and interconnectedness.
Okay, so it's the math of relationships and transformations. How does it map onto the UCTE's layered structure?
The alignment with our layered framework is remarkably direct and elegant. Hypersymmetry itself, that fundamental pre-emergent reality of the Omnilectic layer, can be conceptualized formally as a metacategory. In this foundational metacategory, the objects are the invariant structures, those absolute principles like coherence, entropy, universal constants, and the morphisms represent the fundamental processes themselves, like symmetry reduction and coherence flows. The entire symmetry reduction process, which is central to how complexity emerges coherently from simplicity in the UCTE, is rigorously formalized using functors. Functors are special mappings between categories that crucially preserve their inherent structure, like relationships and compositions. So these functors map coherently from the metacategory of hypersymmetry, Omnilectic, down through the categories representing Hololectic, relational, and derived mathematics. Your example of functor FHR maps hololectic structures to relational ones. They allow us to rigorously show how absolute invariants transform into relational structures while preserving their underlying coherence. And the emergence of tertiary derived mathematics, our everyday math and measurements, is then seen as higher-order constructions, essentially new categories built consistently upon this relational foundation, all linked by these coherence-preserving functors. It provides a mathematical language that naturally describes these layers of unfolding structure and their deep interconnections.
That helps clarify why category theory is so powerful here. It's literally designed for mapping processes and relationships between these fundamental structures. Can you give us a simplified outline then of how such a formal proof might actually be constructed using these categorical concepts and the four layers we've discussed? What would the steps look like broadly?
Certainly. While the full details would be intensely mathematical, the overall structure of a formal proof using category theory would involve defining each of the four layers of mathematics we've discussed as distinct mathematical categories, and then rigorously showing how they relate through these structure-preserving mappings called functors, ensuring consistency throughout. 1. Step 1. Define the Omnilectic category. Hypersymmetry is absolute. Here, the mathematical objects would be precisely defined invariant principles themselves, the entropy, coherence measures, universal invariants like C or H. The morphisms, arrows between objects, would represent the fundamental processes of symmetry reduction and coherence preservation operating at this most foundational level. Step 2. Formalize the Hololectic category, H continuous fields. In this category, the objects are defined as continuous fields, like spacetime manifolds, gauge fields. The morphisms represent the transformations these fields can undergo while maintaining continuity, like diffeomorphisms or gauge transformations. A specific functor, let's call it FOH, would then be rigorously constructed to map the invariance from the Omnilectic layer, O, to these continuous field structures, H, demonstrating formally how the blueprint manifests as fields while preserving coherence. Step 3. Formalize the relational category. R, interactions weights. Here, the objects are defined as relational entities like wave functions, periodic functions, graph structures. The morphisms represent the interactions, correlations, or transformations between them, like quantum evolution or network dynamics. Another functor, GHR, would map the continuous fields from the hololectic layer H to these relational entities, R, showing formally how fields give rise to interactions and waves coherently. Step 4. Include the derived category, D, discrete symbolic. In this final category, the objects are defined as discrete abstractions, such as particles, numbers, specific quantum states, eigenstates, or symbolic representations, matrices, algebraic structures. The morphisms represent higher-order transformations or computations between these discrete units. A functor, HRED, would map the relational entities R to these derived abstractions, D, showing formally how interactions crystallize into discrete, measurable units or computable symbols.
Okay, so you define the layers as categories and the transitions as functors. How do you tie it all together?
The crucial step is to create a commutative diagram. Imagine drawing these categories, OHRD, as points, and the functors, FGH, as arrows connecting them sequentially. You might also have arrows representing composite transformations, like mapping directly from O to D. This diagram is commutative if the result of following any sequence of arrows between 2 points is the same, regardless of the path taken. For example, applying the sequence H, then G, then F to an object in O must yield the same result in D as applying a potentially defined direct functor from O to D. Mathematically, HGFO, this commutativity rigorously demonstrates that transformations are consistent and preserve coherence throughout the entire layered structure. It's the mathematical guarantee of harmony. Finally, the proof would aim to demonstrate universality by showing using established categorical tools like equivalences and natural transformations that all known consistent mathematical systems, like ZFC set theory, arithmetic analysis, can be embedded within this categorical framework derived from coherence. This would argue for its comprehensive power as a foundational ontology. It provides a rigorous, interconnected structure for the entire theory, firmly rooted in coherence preservation.
Given the immense rigor required by category theory, it's crystal clear that the definitions of these core concepts, especially new or repurposed terms like coherence and symmetry reduction, must be exceptionally precise and non-circular for this formal proof to hold water. Can you articulate the refined axiomatic definitions necessary for this level of formal rigor? How are these key terms pinned down?
Absolutely. Clear, unambiguous axiomatic definitions are paramount for mathematical rigor in such a comprehensive theory. Based on the sources approach, here's how they might be formalized. Coherence. This isn't just a vague feeling of harmony. It's formally defined as the inherent alignment and compatibility among components of a system, mathematically ensuring the preservation of consistency, for example, logical non-contradiction, conservation laws, across all transformations and emergent states. In the categorical proof, as we just discussed, it's formally represented by the commutativity of diagrams, which mathematically guarantees that all paths between specified states yield consistent, equivalent results. Symmetry reduction. This is precisely defined as the deterministic coherence-preserving process whereby invariant unified structures, objects in a higher category, differentiate into more specific relational ones, objects in a lower category. It's formally represented as a functor, a structure-preserving map between categories that takes objects and morphisms from a higher category, for example, Omnilectic, to a lower, more differentiated one, for example, Hololectic, explicitly preserving the coherence relations defined in the higher category. Relational emergence. This is the manifestation of mathematical and physical entities, fundamentally, as the relationships, interactions, or transformations, morphisms, between underlying unified principles, objects, rather than as isolated objects themselves. It's formalized by the structure of the objects and especially the morphisms within the relational category, where interactions are the primary elements being mapped and studied. Invariant principles. These are the fundamental unchanging properties or structures existing in hypersymmetry, Omnilectic layer, that are mathematically proven to persist, remain invariant, under the action of coherence-preserving functors across all layers of emergence. They are modeled as the foundational objects in the Omnilectic category. State. Absolute mathematics. This refers to the unified, undifferentiated mathematical structures inherent in hypersymmetry before any symmetry reduction or manifestation occurs. It's formally modeled as the Omnilectic category O itself, representing the state of pure potential, maximal symmetry, and absolute coherence, tertiary mathematics. These are the abstract, discrete, or symbolic constructs that emerge from relational mathematics through well-defined processes of quantization, discretization, or symbolic representation, functors into category D. They are formally modeled as the derived category D. These precise definitions, grounded in the language of category theory, ensure that every term has a clear formal meaning and role within the framework, allowing for rigorous logical deduction and the construction of the commutative diagrams needed for the proof.
Finally, let's clarify one more potentially confusing point. The distinction between symmetry and invariance within this framework, they sound very similar, and in everyday physics language, they are often used almost interchangeably, but your theory seems to give them distinct yet clearly complementary roles. How do they relate specifically in the UCTE?
That's an excellent question, as they are indeed deeply connected, almost like two sides of the same coin. But in our framework, they have precise dual roles. They act as dual aspects of the same fundamental phenomena, which is coherence. Symmetry, in the standard sense, refers to a transformation that leaves certain properties of a system unchanged, like rotating a sphere doesn't change its appearance. In the UCTE framework, symmetry is primarily viewed as the generative principle, or the potential for transformation that exists inherently in hypersymmetry, particularly within the omnilectic layer. Think of it as the action or the rule that allows for coherent change while preserving some underlying structure. It's a possibility encoded in the morphisms of the omnilectic category. Invariance, on the other hand, is the property of remaining unchanged under those allowed symmetry transformations. It's the resultant coherence, the conserved properties or quantities that arise because of those underlying symmetries. For instance, in physics, the laws of physics are Lorentz invariant because they remain the same under Lorentz symmetry transformations, like changing velocity or rotating your perspective in spacetime. The symmetry is the transformation. The invariance is the property that doesn't change.
Okay, so symmetry is the potential transformation. Invariance is the resulting stability. How does the framework formalize this?
In our framework, this duality is formalized quite elegantly using category theory. Symmetry is encoded primarily in the morphisms, arrows, of the omnilectic metacategory, representing the fundamental transformations allowed by coherence at the most foundational level of reality. These morphisms define the rules of change. Meanwhile, invariance is encoded in the coherence demonstrated by the functors mapping between categories, representing the preserved properties and the consistency, the commutativity of diagrams, as systems transition coherently from absolute hypersymmetry O through the hololectic H and relational R layers down to the derived D forms. The functors guarantee that certain essential features carry through unchanged. This approach essentially generalizes familiar concepts like Lorentz symmetry and invariance, which are absolutely critical in Einstein's relativity, to potentially higher dimensions and makes them applicable across all layers of the UCTE, linking the most abstract principles to concrete physical laws through this fundamental duality governed by coherence. It demonstrates how the dynamic potential of symmetry fundamentally leads to the stable, predictable, coherent results of invariance throughout the entire unfolding of reality. It's the universe's way of staying consistent with itself, even as it continuously transforms and differentiates. #outro.
And that brings us remarkably to the end of our deep dive today into invariant omnilectic mathematics and coherence-based physics. What we've explored is nothing short of a revolutionary view, a potential paradigm shift. The idea that the universe and its laws are not just incidentally described by mathematics, but that mathematics itself fundamentally emerges from a self-generating principle of coherence. It begins, potentially, with a single axiom, 001, that seeks to turn a mathematical ambiguity and undefined into the very seed of all structure, resolving deep paradoxes along the way and offering a completely new lens through which to view reality. So here's something to consider as we wrap up. If 0 to the power of 0 truly is 1, and if that fundamental unity, that initial spark of coherence, is indeed the generative source of all mathematical and physical structure, what does that imply for our deepest understanding of nothingness itself? What does it say about the ultimate source of everything we observe? It suggests, quite profoundly, that even in apparent emptiness, perhaps even in the very definition of null or zero, there lies an inherent, powerful, generative potential for reality to coherently construct itself, unfolding layer by magnificent, consistent layer. It paints a picture of a universe that builds itself, not primarily from random chance or arbitrary rules, but maybe from an innate drive towards perfect harmony and consistency. Think about that for a while. We'll be back next time with another deep dive into the fascinating frontiers of knowledge.